And so now we want to talk about context switching in detail. And so the context switch is, as this first sort of statement says, when the contents of the CPU's registers and the program counter at any time, the context is swapped, right? So we take the CPU registers and the program counter state for one task, and we save it somewhere, and then we swap the registers and the program counter for another thread. We swap that in, and so this is the switching part of it, right? So we have the context, and when we do a switch, and so this is a long sort of explanation of it, but then we'll just step through it now and talk about how it's done and when we need it. And so the scenario is that we have here two tasks, task A and task B. And task A is executing on the CPU, has control of the CPU, and then some interrupt happens. And so for those that don't know what an interrupt is some sort of an external signal that actually comes and says to the CPU, hey, this has happened and you need to handle this now. So the CPU gets interrupted by an interrupt, which is why they're named interrupts. And so the interrupt arrives at the processor and says, hey, cool, and the handling function of the interrupt is to call the scheduler, and so the scheduler has then decided that task B needs to run next, and then we want task B to execute. And now the problem is that for those that don't know how CPUs execute instructions, which you'll learn in this course, of course, but next week, is that there are sort of status registers and a bunch of registers that the CPU uses to perform and to carry out the instructions that it's told to carry out. Where it gets these instructions from in memory is stored in the program counter. And so this is just a value that says, hey, yep, you're executing the code that is here in memory, right? So the problem is that we have all of these registers and they have specific values that are tied to the context of a certain task. In this example, we have at the beginning the context of task A is loaded into all of the CPU, and we can't just start task B because we'd lose all of the information in task A, and if we wanted to start task A again, we would have lost the context that we needed to run it. And so the solution is quite simple, and that is that we just take the state of the CPU, the context, and we save it. We load the new context of task B in, execute B until it's finished, save it, or if it's finished, then we don't, and then we load task A again, the context. So how this is exactly done, we can see this is a very basic sort of layout of what a CPU roughly looks like. We have the stack, so this is the sort of temporary memory that's associated with the current execution context. We have the code in memory, and so this is not stored in the CPU. This is stored somewhere in system memory. And so all you use to reference where the code to execute, the code that needs to be executed is the program counter. And so in here will be some address to say, yep, okay, this is the code in memory that you're currently executing. Status register, which shows all sorts of properties of the CPU at that point in time, and is very important to sort of performing of certain instructions and arithmetic and logic and blah, blah, blah. You have a stack pointer, which points to where the stack is, like where in the stack you're currently saving values. And these are the general purpose registers. So these are ones that are generally, or are very common, they are used for implementing logic or performing certain instructions. And so they are required by the CPU. So how context switch happens is that we say, okay, we need to start saving all of this context. So this whole sort of, like all of this here is sort of the context of task A. And so what's going to happen is it's going to push the program counter onto this task stack. Then we're going to go along and we're going to push on the program counter, then the status register and all of the general purpose registers. And then we'll take the stack pointer and push that on. So essentially we've taken all of this, except for the code, and we've pushed it onto this stack. Now this stack is of a set size or something, and then we can just save this in memory. This is somewhere in memory. And so what we can do is that we can just take a sort of a copy of the stack pointer to show where the stack is located in memory, and we just save this. This is what the kernel keeps track of. It says, hey, I've got task A, which is currently not running, but it'll have a copy of its stack pointer to know where it can sort of unpack the context from. And so that's exactly what happens. So this, for instance, is the copy of the stack pointer which points to all of the information. This is this application stack, or the threads, the task stack. Here we have then the program counter and the status register and general purpose registers that have all been pushed onto the stack, right? So this is the actual stack pointer, but we have a copy of it, so we know where it's located. And so then that's what happens, is that the inverse is done, in that the stack of task B is taken and everything is unpacked. So you can imagine we pack up everything in task A. Task A? Yeah. So we pack up the stack. We save it into a copy of the stack pointer. Then we take the copy we have for the task B stack pointer and we unpack it, right? So we know where everything's stored, and we just unpack all the contents back into the CPU, and hey presto, we have the general purpose register loaded to what they should be. The status register is what it was before, and we have everything set up. So finally, the program counter is reloaded, and it can then start pointing to where the code in memory should be executed from. And that's how it's done. And then when it's finished, we just do the same process again. So this is how we get the swapping of tasks into their different states. So I think we've sort of covered everything here. Yep. So then how we actually implement a task this is always slightly different, but on FreeRTOS, a task is a function, and a task is essentially just a loop that should get executed forever. And so if you wanted to implement the network I/O loop, you would just have a task, which is some function, and the function you pass to the function that creates the actual thread task. And then inside of the code for the task, there'll be some loop, because you don't really ever want the loop to end, because the termination of the task is not handled by the code itself generally. It should then somehow signal the scheduler to say, yes, this thread should be, or this task should be destroyed. So that's what's written here. So now we come across the FreeRTOS API and how it actually creates threads. And so it has, there are more calls than this, but the most common ones that you'll come across and the ones that you'll be using are these 5. And so this task create here is, as the name pretty much says, it creates a task. You give it some human readable name. You have to tell it how much memory it's allowed to use, stack size. And so this is very useful in embedded systems, because you can really make sure that tasks are given as little memory as possible if you want to save size. Parameters, because as I said before, the task code is essentially, all you do in here is you say, yep, this is the function that it should run. And if it's a function, it can have parameters passed to it. And so if you want to pass parameters to it, this is the one. And this is very useful if you're creating 4 tasks from the same function, then you can sort of give them different parameters so they all just don't do this exact same thing. And a priority. And the priority is what is used by the scheduler to determine when this task should be run. And then this is the handle that you'll use to reference this task. So it's essentially like saying a pointer. And so it really is. I think it's just a void cast pointer. Then you have the 2 common delay functions, and they are an absolute and a relative delay. And so what that means, it says, okay, pretty much I want you to take my task which is running, and I want it to block for a set period of time before you return it to ready. And so that's what they're going to do. This one's going to say, yep, okay, delay me this absolute from this point in time when this line of code is executed, delay me this many milliseconds. And then this one here is going to say, okay, I previously woke up here, and you can do some sort of a relative delay, saying from this point in time previously, I want to sleep until that point in time plus some increment has happened. Suspend and resume, and we can see these on here. Suspend and resume is what you use to return or to put tasks, if they're blocked or running, into the suspend state, and if they're suspended, you use them to put them back into the ready state so that they can be scheduled by the scheduler. So an example of the task code we can see here, we need to give it some sort of a function, and this is what's passed in here as the task code. And it should have some sort of an infinite loop. And you can see here I have just an empty for loop that's going to run forever. And so this is the code that needs to get passed into X task create, which we can see here. Well, this is a bit hard to get all of this code on this slide. We have a handle, which is also used and put in the end, as we can see here, to reference the task itself, because we'll need to, when we suspend and resume, give it a task handle. So we need to keep track of that. But essentially what's happening here is we're just doing task create, we're passing it in the function that we want to call it, we're giving it some human readable name. I mean, this is just for like debugging or whatever, giving it a stack size, and in this case we've defined this somewhere else. We're giving essentially no parameters in a priority, and so this task idle priority is one of the sort of default lowest priorities you can get in FreeRTOS, and then the handle, and then we can check that it was created properly. And so that's pretty much, and this, once the scheduler is started, this code here would just get executed in a loop.